Hi everyone, my name is Aayush Giri and I'm excited to share a project I have been working on for the past couple of days for the Ethereum Protocol Fellowship. As someone who is passionate about zero knowledge proofs in cryptography, I believe they hold a key to scaling Ethereum effectively. And over the next few minutes, I'll show you how my project leverages cryptography to create a more efficient and secure application. The project actually demonstrates the use of, I'll just get into the presentation as well. So the project demonstrates the use of homomorphic encryption for secure order matching in a financial trading system by utilizing the BFV encryption scheme and homomorphic operations. We can ensure that the process remains confidential throughout. This innovative approach not only enhances the security for the trading systems but also showcases that there can be a future where we'll be creating encrypted mempools for the real world. So let's just dive into the presentation. So this is the problem statement which we have. So in the traditional order matching systems, what happens is that buy and sell orders are processed in plain text, exposing very sensitive financial data to potential breaches. So our challenge is to securely match these orders while keeping the actual order values confidential, thus preserving data privacy. Now, for this is the solution overview, but I would like to explain in two lines like what homomorphic encryption actually is. So homomorphic encryption is something which can be used for privacy preserving outsourced computation. This allows data to be encrypted. As we can see here in this pictorial representation, the data can be encrypted and outsourced to a cloud commercial environment for processing, all while it is being encrypted. And the result of the computations are left in an encrypted form, as we can see here, which when decrypted results in an output that is identical to the produced had the operations been performed on the unencrypted data, right? So this is a visual map which provides us a comprehensive overview of the project from the initial data input to the final output, and it illustrates in each step including encryption, homomorphic computation, and then decryption, and offering a clear understanding of each component's role in the project. So encrypting orders, each buy and sell order is encrypted using the BFV scheme, which ensures confidentiality. We can see that it has been outlined here. So when we start from there, then we initialize the BFV scheme parameters which are needed. Then we generate BFV parameter schemes like the T modulus and the slots numbers, which is the power of polynomial which we'll be using, and I'll be explaining it in more detail in the next slides. But for now, I'll just explain the flow, like what is exactly happening. So the initial BFV scheme parameters are set. Then we generate a secret key and an evaluation key, which is essential for the BFV scheme. Then we parse the buy and sell order from the orders.json file, which I'll show you in the code. And we pass the data in a struct of this form, where struct is in a it is named as orders, and it has buy orders and sell order vectors, and pair is a string. Now we encode these buy orders and sell orders so that they can be then mapped to the plain text ring. We are using ring data structures in background, which are from a library, right? So we encode them and then we encrypt them. So this is the part from where BFV homomorphic scheme starts, and then we'll sum up the orders. So homomorphic addition is performed to sum the encrypted buy and sell orders separately, and then we compare the sums. So the univariate less than function compares the encrypted sums to determine if the buy orders are less than the sell orders without decryption. So after that, if it is yes and it is no, and in the same time at this point we decide the transaction volume and the addressable transaction volume. So based on the comparison, the transaction volume is set and ATV is the addressable transaction volume. We'll go through these in the next slides as well, and I'll show you in the code also. But for now, we'll just keep this in mind that ATV stands for addressable transaction volume and TV stands for transaction volume. And after this has been done, based on what values these variables get, we fill the sell orders based on the ATV, and buy orders remains the same in this case, and the vice versa happens here. And after that, we decrypt the orders which are which have come up as a result, and then we decode them into plain text and we print the result. So this is a high level walkthrough of the code. Like these are some encryption parameters which are set up, as I said. And this is a very important function which we'll see in the code also, and I'll explain in the slides as well. So let me just go to the code base. So this is the code base, and as you can see, like these are the few parameters which are set: plain text modulus and number of slots. After that, we are generating the keys, as I said, and it is this order.json file which we are using to pass the data, and then the data has been passed in the struct, extracting the buy and sell orders. You can see that this is the buy and sell orders array in the orders.json file. Now we'll do the formatting, which I mentioned here in the flowchart. This is the part where we are formatting and encoding it, right? And after that has been done, we'll go to the encoding section and encoding of both buy orders and sell orders, then encrypting both buy orders and sell orders, and after that we are summing up the values, and these are, as you can see, these are ciphertext, right? So the whole computation is happening over ciphertext. After comparison has been done, we create two variables. One is transaction volume and one is the addressable transaction volume. So addressable transaction volume will be the value which is lesser in number. For example, in this case, the sum of 66666 comes out to be 36, and the sum of 1 2 3 4 5 6 comes out to be 21. So the sum 21 is the addressable transaction volume in this case. So we'll fill the buy orders based on the sell orders, right? And this is just a match statement which we put up here so that we can see how it is happening, and I'll run the code as well. I'll first finish the explanation what is happening. So the code is entirely how the flowchart depicts. So this is the univariate less than function. Now the function starts by subtracting y from x to obtain z. It then calculates z square and its higher powers using homomorphic multiplication and relinearization. Next, it evaluates a polynomial g z square homomorphically using pre-computed coefficients, and finally returns a ciphertext indicating whether x is less than y or not. So this approach ensures the comparison is performed securely without decrypting the data, right? So this is an example scenario for the order.json file which we have. Like this is the buy order and this is the sell order. So we'll first encrypt both these things. Encoding is also there, but I'm just skipping that step for now. So we are just encrypting the orders, and then there is an encrypted buy order and encrypted sell order formed like this. After that, we are summing the orders and performing homomorphic addition. This addition is called homomorphic because we are adding the values which are encrypted, that is, these are ciphertexts, right? And we'll see them in the CLI also, like how the ciphertext shows. Then we are comparing them, and let me remind again, everything is happening, all the computation that is happening is over a ciphertext, not plain text. Then we determine the transaction volume, and this is the transaction volume, in our case 36, and the addressable transaction volume which can be filled is 21, that is the lower value. And then based on this, we'll subtract from the addressable transaction volume while filling the orders, and we'll put 0 in the case when the orders cannot be filled, right? So this is what the output we should get for this case. So let me just go to the code base and we'll run this example. This is the order.json file. I'll create a new terminal. I'll go into the folder and I'll do cargo run. As you can see, we are comparing the result, and this is the comparison result. This is 0 because the value is coming from the univariate less than function, and we can see the transaction volume is 36, addressable transaction volume is 21, and we are filling the buy orders using the sell orders because the sell order sum is less, right? And these three cannot be filled because this value is 21 and this is 36, as you can see. And buy orders are decrypted after everything has been done, and this is the order matching process. So this is the demo, and after this In conclusion, homomorphic encryption enables secure computation on encrypted data, ensuring confidentiality. And the BFV scheme, in this case, allows us for homomorphic addition and comparison, making it deal for secure order matching and transaction volume calculations. I've been working on the Nethermind client implementation as well. I'm trying to learn it, but I could not really understand it in a much depth as far as till now. But I really want to work on how Ethereum protocol works internally, and would want to learn and contribute to the zero knowledge scaling part of Ethereum. I mean, I believe that is the future, and this project which I have built is like, think of a future where we can have an encrypted mempool where there would be a case that no one can have an MEV opportunity, as far as I can understand, and that would be very good for the users. I mean, no one would have to think about slippage and all those things. So yeah, so this is the project, and so this is the presentation for Ethereum Protocol Fellowship, and I hope I get selected. So yeah, that's it. Thank you guys.